Okay, so take a moment to write this down while I'm going to comment on what you actually see here on this example. So this is a linear homogeneous system with constant coefficients, right? So I wrote it again in the traditional form by components, but just so you know, from this point on, we will rarely need to go back to this component format. We will just work directly with the matrix format. Because the way we develop the solution will be using matrices. Although there will be a particular moment in the next lecture when I'm going to go back to this format just to explain briefly the connection with the eigenvalues and eigenvectors. To anticipate a little bit, the starting point of solving this system is going to be finding the eigenvalues and vectors of this matrix, which you should be already familiar with from the linear algebra class, the 1 hour linear algebra class that is required, or you have to take it at the same time with this class. Nevertheless, I'm going to still go over briefly on how to find eigenvalues and vectors, at least in the 2x2 case, because that's what we need in the case of a square matrix with 2 rows and 2 columns. But I would assume, though, that you actually have some exposure from that course that you have to take for this class, and you should be able to find eigenvalues and vectors even if I don't say anything about it, which I won't. I mean, I will go over some of the steps involved. But what's not clear maybe is the connection between the two. So rather than just go over the formula directly and say, okay, find the eigenvectors values and throw in the solution, I'd like to take some time to explain the why these eigenvalues and vectors arise naturally when you try to actually solve a linear system of equations. So for now, make sure you understand how you go from the traditional way of writing a system by components to the matrix form. And if that's not clear, go back again to the previous parts and try to understand, and if not, of course, ask questions in the office hours if you still have questions on the notation. So that's the matrix form. Obviously, it's in the form x prime equals ax, and so the matrix of the system is just 1, 1, 4, 1. I should mention also, because sometimes this notation is confusing, you see I denote typically the unknown, the dependent variable in the vector form, by x bar, and you may wonder if it's a duplication of notation. I mean, that's a valid criticism, I suppose, but remember, we rarely need to go back to the components, so it doesn't really matter how you call these components. You will see some examples in the book. They call them x1, x2, or other letters. As long as you make sure you put the bar on the top to indicate clearly that's the column matrix, then that's difference enough, I suppose, because most of the time we're going to work with the dependent variable in the form of a column matrix anyway. So take for granted now the general solution is this. As I mentioned before, it will always be as a linear combination of two independent solutions. Now, there are other forms of the general solution. You already can look at the formula sheet and you will see there are also more complicated forms with cosine and sine in the complex eigenvalues case. But even in those cases, you still identify two independent solutions in a linear combination. One different way of writing it is to actually pull out e to the 3t via scalar multiplication. And this is actually the notation I would like sometimes, because it's very suggestive in the way you obtain it, as you will see later. So remember, scalar multiplication means that you can multiply a matrix by the same scalar. So conversely, you could pull out the common factor of all entries if you have such a common factor. Both entries here have e to the 3 as a common factor, so I can pull it out via scalar multiplication. Scalar multiplication in reverse if you want, right? So 1 times e to the 3t, 2 times e to the 3t, I can pull the e to the 3t out of the matrix. And same thing for the second component of the solution. In the formula sheet, I actually give the solution in that form because, as you will see again later, in the next lecture, in this form you can clearly identify the eigenvalues and vectors for this matrix. So you can take a minute if you want to do as an exercise, if you want to find the eigenvalues and vectors, you will see those are actually 3 and minus 1, the coefficients of t, and the corresponding eigenvectors are 1, 2, 1, minus 2. But we'll have time to discuss that later. I'm just saying that there are multiple ways to write the solution. This is the one I like because it shows you immediately, the main components of how you actually obtain it. On the other hand, if you actually want to use the solution for some other stuff, you may prefer this format because it's more compact. And so in fact, I'm going to use this format to verify the solution. So let's actually check that these independent solutions, e to the 3t, 2e to the 3t, and the other one are solutions indeed. This is just, they will be, because obviously I did it before, but just to see the steps involved if you want to check it, and maybe to again practice a little bit with the matrix form of dealing with linear systems of differential equations. So this one, e to the 3t, 2e to the 3t, how do we check that it's a solution of the system? Well, we plug it into the system and do the work, right? So we're going to plug in this x1 prime on the left side, right? So we're going to take the derivative of e to the 3t, 2e to the 3t. And on the right hand side, we're going to have to multiply by the matrix. So 1, 1, 4, 1, e to the 3t, 2e to the 3t. So it's just like in the single ODE, except that you have to do the work now involving matrix operations to verify that this is indeed a solution. So on the left, remember when you have a derivative, on top of a vector, it means you take the derivative of both entries, right? So that means on the left side, I have 3 to the 3t. On the right hand side, on this one, on this component, it's 2 times 3, the derivative. 6e to the 3t. And here we have the matrix multiplication. So we have 1 times e to the 3t plus 1 times 2e to the 3t. And then 4 times e to the 3t plus 1 times 2e to the 3t. Add the 2, 3 to the 3t, 4 plus 2, 6e to the 3t. So the left and the right matches, as expected. Okay, so obviously you don't do that if you're confident, of course, your work is correct, right? If you know that you use the formula correctly, then you just write it down, but you could always check to see if you're right by plug it in back into the equation. Let's do the other one. Let's check the other component of the solution. This one, e to the minus t minus 2e to the minus t. So again, we're going to plug it in the left side of the system. Take the derivative, and on the right hand side, we're going to multiply it by the matrix of the coefficients. The derivative minus e to the minus t. Here we have a double negative, so be careful. Minus 2 times minus 1 becomes 2 e to the minus t, right, when you do the chain rule. Now the matrix multiplication, we have 1 times e to the minus t plus 1 times minus 2 e to the minus t. And now the second row times the column, 4 e to the minus t plus 1 times minus 2 e to the minus t. Okay. So we get here 1 minus 2 minus e to the negative t. 4 minus 2 becomes 2 e to the minus t. So obviously both of them check, they are solutions. And since they are independent, they obviously for the general solution of the system. One thing to keep in mind before we move on, like I said, to fully solve the homogeneous system, you need 2 independent solutions. what makes them independent, so maybe we should write it here. So to be independent, this is just anticipating a little bit. To be independent, we need either the exponents of E to be different, or the vectors multiplied by them. That's basically a verbal description of me saying you need either different eigenvalues or different eigenvectors. Again, we'll deal with that when the time comes, but I just want to point out what we mean by independent anyway, right? I mean, independent means that one should not be a multiple of the other, essentially. So that's achieved immediately, of course, if you have different exponents. That's typically what happens. Not always, of course, but if you have different exponents here, that is to say if you have different eigenvalues. Or you could have a single eigenvalue but different eigenvectors. Although in the 2x2 case, that's a nearly trivial case, so I'm not going to focus too much on it. I'll just mention it at some point, so you know that it exists, right? I mean, what typically happens is that once you have different eigenvalues, you have different eigenvectors. Not always, but in the majority of cases. The complex case satisfies this requirement as well, because you always have two different complex eigenvalues, two different ones, always. They come in conjugate pairs. And then you can have a single eigenvalue, and that requires a special way to deal with a second independent solution. It's a really nice analogy with a single ODE of second order homogeneous. Remember, we had distinct, in that case, if you remember, you look at the characteristic equation, you had distinct real roots, you had complex roots, both of them provided you with two different independent solutions, and there was the double real root, which was a special case, and we went through some work to show that there is a different way to provide the second independent solution. So the same thing here will happen when we have a single eigenvalue. You need a different way to obtain the second independent solution. But otherwise, the main theory essentially follows the same pattern as in the single second order ODE. So that's it for today. Just to warn you, the second lesson will have multiple parts. It's much longer than usual because it's split typically in multiple sections. But in order to be self-contained for these presentations, I'm gonna make them part of a single lecture, because the goal will be to solve the homogeneous system, except that, as you'll see already in the book, this is actually split into two sections. So do not expect, of course, to cover this in a single setting. It will be like a single lecture with multiple parts, but you will split those parts into at least 2 days in order to have time to absorb the material and do the homework. So that's it for today. I'll see you next time.